In this video, we'll carry on with the elimination mechanism for our third part, and I've got two different halogenoalkane compounds here. Here's a primary halogenoalkane and a tertiary halogenoalkane. This primary halogenoalkane is resistant to elimination because the adjacent carbon does not have any hydrogen atoms bonded to it. Therefore, there are no adjacent hydrogen atoms. So this compound, because we have no hydrogens on the adjacent carbon, it is resistant to elimination. Just like a substance that is one carbon, like halomethane, for example, a halomethane cannot be eliminated because, again, there are no adjacent hydrogen atoms. And this compound here is a tertiary halogenoalkane. It's a completely asymmetric tertiary halogenoalkane. It's also chiral for when you get to that. Now, I'm not even going to bother drawing the lines because it is a bit more complicated to represent my hydrogen atoms. I want to show it in as simple as possible way. Now, this halogen, there are three adjacent hydrogens possibilities. This carbon is adjacent, this carbon is adjacent, and this carbon is adjacent. So these hydrogens here, there are three possible elimination bodies, three hydrogen atoms that could be removed in the acid-base reaction with the basic hydroxide to produce different alkenes. Now, if I just sketch them out very quickly, this is 6 carbons long. There's a methyl group on the third carbon. We are going to eliminate the halogen and, let's say, form the double bond that way. Or I could eliminate that way. They are different compounds. Or I could eliminate with my third potential elimination buddy, adjacent hydrogen atom, like so. And that gives me 3 different products. Or does it? Whenever we have alkenes, we must always be aware, do they exist as geometric isomers? So we know they've all got a double bond, so there's limited or fixed rotation around that double bond. That won't rotate. I cannot rotate around a double bond because a single bond will freely rotate. Check that out. The double bond, I cannot rotate. I'd have to break it in order to rotate it to form the other isomer. So this first one here, does this carbon have 2 different groups bonded to it? Yes, it does. It's got the methyl group and a hydrogen. What about this carbon? It's got a methyl group and a propyl group. So this exists as E and Z isomers. What about this one? This carbon of the double bond has a methyl group and an ethyl group. So they're different. And this carbon of the double bond has an ethyl group and a carbon. And a hydrogen. So this also exhibits EZ isomerism. My third isomer down here, first carbon on a double bond, it's got an ethyl group and a propyl group. They're different to each other. And the other carbon, has 2 hydrogens. So this one does not exhibit geometric isomers. There are therefore 5 products from the elimination of this 3 halo, 3 methyl hexane. The 2 isomers, the 2 geometric isomers, the E and Z isomers of 3 methyl hex-2ene, the 2 geometric isomers of 3 methyl hex-3ene, there is only one 2-ethyl pent 1-ene isomer possible.